Another great example of conservation of energy are slingshots. So a slingshot is pulled with an average force of 70 newtons for 90 centimeters. Nice try, Mr. Dewick. Cross out the 90 centimeters. How many meters? 0.9. Did I give you less than 6? I forgot. Terrible of me. Okay. Justin, what does A want me to find? Now, this potential energy, if you're using a slingshot, look at the picture. Is this MGH? Is there a change in height? This is potential energy just as stored energy. A lot of students, for a slingshot question, they want to say, oh, the potential energy is MGH. You didn't give me a mass, Mr. Dewick. And they want to use the 0.9 as the height. That's not a height. So how can I figure out how much potential energy? Well, another way to store energy is to do work. Justin, did they give me a force and a distance? And the force and the distance are in the same direction? Well, hey. I should be able to do that one in my head. 63 joules, double check me. So this is not MGH potential stored energy, but this is stored energy nonetheless. Where is it stored? In the bow, or in this case, in the slingshot. Not a bow now, slingshot. Ooh, suppose you put a 35-gram mass in the pouch. How fast will it leave the slingshot? Now I can use conservation of energy, but I'm going to use a simplified version. I'm not going to write out the whole equation. What is all of the potential energy going to turn into? What type of energy? When I let go of the slingshot, where is all that stored energy going to go? Someone said it. They're right. Kinetic. Okay, so as this, I could do a full conservation of energy, but I think I'm going to, as a shortcut, argue that all of the initial stored energy turns into the final kinetic energy. I think once you let go, there's no more energy stored in that slingshot once the rubber band snaps the rock forward. So I'm going to argue that 63 equals a half mv final squared. I guess I should have crossed out that 35 grams. How many kilograms is 35 grams? Give you a hint, there's going to be a 3 and a 5 in the answer. 0.35? It's 0.0. You got to always be careful with grams. I always got to be careful. It's 1,000 grams into kilograms, so it's divided by 1,000. It's 0.035 kilograms. Anyways, how would I get the V by itself? I guess times by 2, divide by m, square root. 2 times 63 divided by 0.035. Oh, this works out nice. Even. 60, yes? No? Yes? Am I wrong? 60? I got one thumbs up. Okay. And that seems reasonable. I had slingshots when I was a little kid. They go pretty fast, but not so fast that you can't see them. 60 meters per second, that's about half the football field in 1 second. So, yeah, that seems good to me. Tarzan weighs 82 kilograms and he can run at 8 meters per second. Tarzan runs along the ground and grabs a vine, swinging into the air. What maximum height does he reach? Dulp. Okay. Here's Tarzan. Running. Okay. And I guess VI is 8 meters per second. Here's the vine that Tarzan's going to grab. And when he grabs it, he's going to swing up. And I guess that's the height they want us to find. Oh, it's a rope swing. If you look at this question here, is there a change in height? Is there a change in speed? Is there a yucky curvy path? Conservation of energy. KE initial plus PE initial equals KE final plus PE final. Initial plus initial equals final plus final. Are any of these 0? Well, let's look at them one at a time. Now I'm going to get fussy. You're right and wrong at the same time. I would argue that the ground is right there. But wait a minute. Can't we put the ground wherever we want? Let's put the ground right there. And so, yes. I also heard you say, ooh, center of mass. We'll come back to that in a second. There's one more thing that's 0. At the top of the swing, maximum height. At the very top of the swing, how fast will he be going for a split second? Oh, hang on. I did that wrong. Crossed out the wrong one. That would have been a problem. And so what I end up with is a half mv initial squared equals mgh final. Elias, you said center of mass or something like that. Do I need to be worried about center of mass or anything like that? Is there an M and everything on the left? Is there an M and everything on the right? So not only if Tarzan runs at 8 meters per second, we can figure out how fast Tarzan will swing up. If Tantor the elephant runs at 8 meters per second, assuming the vine doesn't break, we can figure out how high Tantor the elephant will swing up. The mass here is irrelevant. How would I get the H by itself? Divide what? Divide the G. And I get this. I would probably write it like this. H final equals, so there's a VI squared, there's a G. You could either, look up everybody for a second, you could put a 0.5 there and I'll give you full credit. I usually just put a 2 down there and don't bother writing the 1 from the 1/2 because to me that looks prettier. On the left, that's messy. That's H final. So it's going to be 8 squared divided by 2 times 9.8. And I get 3.27 meters. Anybody else? Yeah. So not only can we use conservation of energy to look at roller coasters, woohoo, slingshots and rope swings are also great examples of conservation of energy. Or even swing sets for that matter. On a swing set, right? How do you go higher on a swing set? By shifting your weight and moving your legs the right way. You all learn how to do this when you're about 3 or 4 years old, and by tugging on the chains or the ropes at the right time. What you're actually doing is you're adding energy to the system. Where is that energy coming from? The food that you ate. So that's not a closed system. You're adding energy to it. But you learn that at the top of the swing for a split second, how fast are you going? That's when you have your maximum height. Maximum kinetic energy is at the bottom of the swing. Swings are fun. Slap shots are great examples of energy transformations. Put your pencils down and look up. Next page. A roller coaster below has a mass of 255 kilograms. If the coaster just barely makes it over the first hill, how fast will it be going at location B? How would I solve this? Conservation of energy. Change in height, change in speed, yucky curvy path. Okay, so I'm going to start out going, you know what? I'm going to write the law of conservation of energy right here as kind of my template. And then, Elias, what I'm going to do is just adjust it for each question. Specifically, what I'm going to say is, which ones are 0 for part A? Which ones are 0 for part A? So let's look at kinetic. Are we ever at rest? Yes. Our initial? Okay. So the equation simplifies to that, which is really pretty clean, considering if we tried to do this with forces, Emma, oh, ugly, calculus, ugly. Here, that. And in fact, I'm going to get mgh initial equals a half mv final squared. Ren, have you been on a roller coaster before? Yes? Before you got on the roller coaster, did they make you stand on a scale? Did they have to measure your mass? Why not? Because it turns out if we ignore friction, m's cancel. Well, I'll tell you the one that I'm still puzzled with. So Playland used to have what was called a wild mouse, which is a brick. Okay, those are roller coasters that don't go up and down; they go from side to side. Okay, Disneyland has one. It's called Goofy's Sky School. I think it's in California Adventure. It's those ones where you swear you're going over the edge and then it turns you real quick. The Playland ones, I went on those. They had sandbags in them, which means there's something there where the mass wasn't canceling. And my question was always, how did they figure out that the mass doesn't cancel? Why would they have had to add sandbags? What went horribly wrong here that caused them? I'd like to know. Anyways. Times by 2 to get the VF by itself. Or divide by 0.5, I don't care. Oh, actually, that gets the VF squared by itself. How to get rid of the squared? Square root. So I'm going to get the square root of 2 times 9.8 times 18. And I'm going to get 18.8 meters per second. Just for giggles, times by 3.6. Around 70 kilometers per hour. Okay. That's a bit of a meh, but not too meh. That's not bad. I'll go on that. B. Suppose instead of starting at rest, we have an initial speed of 22 meters per second. How fast are we going to end up going at location B? Well, here, I think it's going to be the initial kinetic and the initial potential. That's what gives us our final kinetic. I'm arguing, AJ, that potential energy final is still 0 on the ground, but this time we didn't start at rest, so I better have the half mv initial squared. AJ, have you gone on a roller coaster before? You have to step on a scale before you went on the roller coaster? Okay. Here, I'm going to clear fractions, Elias, because there's a 1/2 in front of that, and there's a 1/2 here. I'm going to cleverly go times by 2, times by 2, times by 2. Those will cancel. Those will cancel. And I end up with VI squared plus 2GHI equals VF squared. I really ended up with VF squared equals VI squared plus 2AD, because G is an acceleration and H is a height, D. Square root. So this time, 22 squared plus 2 times 9.8 times 18. Are we going to be going way faster at the bottom now? Let's find out. Oh, that's better. 28.9 meters per second. How fast is that? 100 kilometers per hour? Okay, that's pretty good. We're going to skip C. We're going to do example 4. A 75 kilogram cart and rider start from rest. I would probably mentally underline the phrase from rest on a 20 meter high ramp. At the bottom, the car is traveling at 15 meters per second. How much energy is lost to heat? Okay. Is there a change in height? Is there a change in speed? Is there a yucky, curvy path? No, but are they asking about heat? This is a job for conservation of energy. My equation is going to get modified. It's going to look like this. KE initial plus PE initial equals KE final plus PE final plus heat. Yep. I know, you were zoned up. Because what are we finding in part C? Heat? Here. Yep. I guess I can say this. Kinetic is 0. Ooh, and I can say potential final is 0. So the heat... How would I get the heat by itself? So you're telling me it's going to be potential initial minus kinetic final? Yep. Here's the total energy we started with because we had no kinetic minus whatever is in the moving vehicle. Whatever we're missing must have gone into heat. So it's going to be mgh initial minus a half mv final squared. AJ, does the mass cancel this time? Is there an m in this term? Is there an m in this? Ooh, is there an m in the heat? Doesn't cancel. So I fibbed to you a little bit, Ren. As long as we grease the roller coaster down and keep the heat from friction to a minimum, then the mass is negligible. But technically, the masses don't cancel. Heat is going to be m 75, G 9.8, H. Ooh. Gonna use the 20 or the 60. Why? And because we're really using our definition of work, force times distance have to be in the same direction. Which way is gravity running? Vertically. Better use a vertical distance. Minus 0.5 times 75 times 15 squared. I get 62.5. Yeah. And that would be joules of heat. Ooh. Cool. Emma, what's B want me to find? So when you say the average force of friction, don't write this down. My first thought would be to say it's mu times the normal force. But did they give me a coefficient of friction? Eesh. Did they give me a normal force? Eesh. My next thought would be, well, what did I just find? Maybe I can use that. What did I just find? The work done by friction. Another term for heat is the work done by friction. So I can say that heat is the force of friction times distance. Emma, how would I get the friction by itself? So it's going to be the heat divided by the distance. It's going to be 62.5 divided. Ooh. Which one am I going to use? Why the 60? Because it has to be in the same direction as the force. Friction is acting in this direction. Well, then I better use the distance in that direction. Why did I say average force of friction? I'm not convinced that it's constant. I suspect it depends on how fast you're traveling. The faster you go, the more energy you're losing to heat. We can't handle that because the changing force needs calculus. And I get 104. Ooh, force. Rube Goldberg machines are great examples of energy transformations, chain reaction machines. And you may already have noticed I love a good chain reaction Rube Goldberg machine. Put your pencils down. This one is called the Blue Marble. There it is. Where was it? If you haven't figured it out, keep your eye on the blue marble. That's the one that's got to get through this whole thing, right? Pretty good. When you bounce a basketball, that's a great example of the law of conservation of energy. I'm going to stay back here so you can hear me talk. So when you dribble a ball, at the top of its bounce, what type of energy does the ball have? Potential. So you can write down here PE, or potential, for part A. Technically gravitational potential, but I know what you mean. When the ball hits the ground, what type of energy does the ball have? Kinetic? I notice that if I don't add energy to the system, a ball loses energy on each bounce, loses height on each bounce. Does that violate the law of conservation of energy? Oh, okay. No, comma, energy is transferred into sound and heat. So here's the question. Is it possible for me to drop this ball underhand like I'm holding it and have the ball bounce higher than its initial height? Can I ever get it to go higher than its initial height? Disagree. If it went higher, wouldn't that mean that it had gained energy from a magical source? So the answer for D is no. But underneath that, if you want to, you can write, unless we are really clever and cheat. Pause the video for a second.
Check out how high these different balls bounce. The basketball, the super bouncy ball, and the golf ball. Now I'm going to try the golf ball on top of the bouncy ball on top of the basketball. And then I'm going to explain how it's related to a supernova. Did you see that? Probably not. So here it is again. The golf ball bounced to 28 feet. We dropped it from about 3.5 feet, so it went up 800% of its dropped height. In fact, if you consider that by itself, the golf ball bounces about 70% of its dropped height. It went as high as if it had fallen from 40 feet up. That is awesome. So how can we get the golf ball to bounce up with that much energy? Let's simplify it to these two balls. When you drop them individually, each ball starts out with some potential energy from the height of the drop. As the balls hit the ground, some energy goes into heating up the ground and some goes into heating the ball. Because that energy left the ball system, you can't get back up to the same height. But when you combine them, the tennis ball goes higher than its dropped height. Way higher. Where does it get the extra energy? As the basketball bounces, it compresses, storing elastic potential energy. As it releases, it springboards the tennis ball upward just at the right moment. This is like the double bounce on a trampoline when you jump right before someone else. You prepare the elastic of the trampoline by stretching it and storing energy, which can then bounce the jumper even higher. In the same way, the basketball stores energy in its compression and is able to push the tennis ball. But just like the double bounce preparer, the basketball can't go as high. You can see that here. It bounces even less when 3 balls are dropped together. Also, during that transfer of energy, some momentum transfers from the basketball to the tennis ball. And since the basketball starts with way more momentum because of its larger mass, the tennis ball's velocity increases by a lot, and it flies up, up, and away. Now back to the triple super ball bounce. Now you get the energy from the basketball's bounce being transferred into the bounce of the super bouncy ball, which is then transferred to the golf ball's bounce. You put the same amount of energy or momentum from 2 more massive objects into a smaller object, and it will go much faster. epic, just like the explosions of a supernova, which may seem unrelated, but what we just did is analogous to the process that occurs during the explosion of a supernova. Just like our more massive basketball transfers momentum to the smaller balls, energy from the dense core of the supernova is transferred in a shock wave that moves through the star to the less dense layers and accelerates them outward at a super high velocity. More massive or denser layers in the core of the supernova begin to collapse when fusion stops there. The collapse is halted when the neutrons in the core actually touch, sort of. This causes the implosion to rebound and bounce outward. You end up with a dense core left behind and these wild outer shells of star exploding outward. Pretty cool. And of course, if you try this at home, which you should, you have to make sure the balls
Outdoors.
are perfectly vertically aligned because any off-centeredness gets amplified by the 2 points of contact, which is why we sadly couldn't get the quadruple tower of balls to work. But if you put a little ring of hot glue or something similar on the balls, it helps to balance them. Happy physicsing!
They couldn't get 4 to work. I tell you, they did not try hard enough. Of course you can get 4 to work. It just takes a little bit of doing. Pause the video. Almost done. A golfer wants to hit his drives further by increasing the kinetic energy of the golf club when it strikes the ball. What would have a bigger effect of the energy transferred on the from the ball, to the ball by the driver? Doubling the mass of the club head or doubling your club head speed? Kieran, why? In fact, doubling the club head speed, 4 times the energy. In theory, you'd get 4 times the range, the distance. Air resistance and things would make it messier than that, but you'd certainly get more than twice the distance as compared to just doubling the mass where you would get twice the distance. Yeah, absolutely. And I think I went on my rant and I mentioned to you, that's why equipment's gotten lighter over the years, not heavier, right? What's your homework? Number 1? 2 is good. 3 is good. 4 is good. 5 is good. Skip 6. Skip 7. Sure, 8 is okay. Skip 9. 10 is okay. Skip 11. 12 is good. Skip 13, but got to go on the roller coaster. 14 is good. Okay. Class is yours, my angels.